Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuits. We will start from where we left in the previous turn. We had actually seen that the gain depends upon the overdrive, and we saw from the previous turn that when the device is in saturation region, right, when the device is actually in the saturation region, then you do have a profile here, and therefore if you look very carefully, that this is the saturation region which we are talking about, this one, this is the cutoff and this is your triode and this is the saturation. So, if you bias your device somewhere here, right, somewhere here with this to be as the V in and this to be as V out, right, this will be V in, right, then I will be able to achieve a gain which is given as AV was equals to, if you remember correctly in your previous turn, to be equals to minus RD times mu n C oxide W by L into VIQ minus VTH. VIQ is nothing but the input at this point Q, right, and this is therefore the nothing but the overdrive, V overdrive, right. So, AV voltage gain is therefore proportional to RD and also onto the overdrive, V overdrive. So, higher the overdrive, more will be the gain, and of course higher the RD you will also get a gain. But you see you have a minus sign here, negative sign, which tells me that a MOS device, when you have a source grounded condition, will always have the output 180-degree phase shifted, right, phase shifted as compared to input, right. So, you will always have a 180-degree phase shift and therefore, it will always be negative in nature. So, if you have input something like this, right, then the output will be output, if you want to find out the output will be something like this, that it will be like this, it will go like this and then like this and this. So, it is 180-degree phase shifted, this is a V out, right, and this is a V in, right, V in. And if you want to find out the gain, it is basically V out by V in at any particular point. So, it is 180-degree phase shifted. Now, let us come back to our original discussion and see how does this works in the triode region, right. So, what we will be doing is we will be now discussing what is happening at the triode region. So, let me erase some part of it and just give you an idea about the basic functionality here, that if you did have a triode region, we saw that the gain in the saturation region is independent of the applied input voltage, it only depends on the value of RD and it does not depend upon anything else, right, it depends upon the overdrive voltage as well. So, with this discussion, let me come to the region. Let us suppose this is point B and this is C, this is A, right. Let me discuss about the point region BC, which is this point, right. This is actually a triode region of operation, triode region. In the triode region, if you see very carefully, then input voltage is obviously larger than threshold voltage, because already input voltage, threshold voltage is somewhere here, or somewhere here is the threshold voltage VTH. So, your input voltage is obviously larger than threshold voltage, but what has happened is that your V out has actually fallen below V in minus VTH, and that is quite critical, that your V out has fallen below. So, your idea was that VDS should be greater than or equals to VGS minus VTH for saturation, but once your V out falls below V in minus VTH, right, then you are in a fix that now the condition for saturation will not be applicable. Now, the device will start behaving like a resistive network or a resistive device, and therefore, I can write down in this case ID to be equals to mu n, right, C oxide W by L, right, and then we write down V in minus VTH into VO, I will tell you why, into half VO square. Why? Because if you remember the previous discussion which we were doing, MOS device was something like this, right, and you did have a RD here and this was your VGS and this was grounded and you are taking the V out from here. So, if you take V out from this to ground, it is exactly the same as drain to source, because source is grounded. So, therefore, VDS is equals to V out, and that is the reason we change from VDS to V0, right, and V0 is the V out which you see from here, where V0 is exactly equals to VDD minus ID RD. So what I do, I just put the value of V0 equals to VDD minus ID, I just plug it from here and place it here, and we write down to be equals to mu n, right, into RD into C oxide into W by L into V in minus VTH into V0, assuming that my V0 is very small. So, if V0 is very small, V0 square will be negligibly small, and this can be approximated to be equals to 0, right. For example, V0 is say 0.01 or so whatever, then if you multiply it 0.01, I get 1 into 10 to the power minus 4, and so it is very small as compared to these quantities here, and therefore you can safely say that V0 equals to VDD minus this whole quantity into V0, right. So we can write down, therefore with this explanation we can write down V0 to be equals to VDD, right, VDD divided by 1 plus RD times mu n times C oxide into W by L into V in minus VTH, right, and you get this, right. We defer to as RDS as the drain to source resistance as 1 by mu n C oxide W by L V in minus VTH, and therefore I can write down V0 to be equals to VDD, right, VDD into RDS into RDS plus VDS RD. How did I do that? See, simple. If you look very carefully here, if you take RDS to be equals to this quantity, because RDS is 1 by this quantity, RDS is the drain to source resistance of the BOS device in the on condition. So, once this is true, if you place RDS here, so this quantity can be written as 1 by RDS, remember. So, I can write down V0 to be equals to VDD, right, upon 1 plus RD by RS. So, if you take an LCM and do all sorts of manipulation, VDD comes outside, this in denominator will come in the numerator, and I will get RS into so on and so forth. Whatever finally get is this thing. So, I will get V0 equals to VDD, right, into RDS upon RDS plus RD. RD is the resistance on the drain side, and it if you look very carefully, this is how it should look like also, because when we were discussing just now, if you look carefully, then this is VDD, right, and this VDD is been broken into two parts as a voltage divider network, and these two parts will be inversely proportional to the resistance offered by this as well as this. This is RDS, so this is basically your RDS, right, and therefore RD, and since they are in series to each other, so the total current flowing through circuit will be nothing but VDD by RDS plus RD. This you multiply with RDS to get the voltage at this particular point, and that is what you are getting, that V out is equals to RDS upon RD plus RDS plus RD. Typically what you get is that RDS is very small as compared to capital RD, and therefore we write down V0 to be equals to VDD, right, divided by or RDS, right, by RD. This is your output voltage which depends upon VDD into RDS. Now, as you can see very carefully or interestingly, that V0 here is actually independent of V in, right. So, if you want to find out del V0 del V in, this will be actually equal to 0, because you do not have any V in on the right hand side, but it depends upon the value of VDD, RDS and RD. Clear? So, as a result, I want to stress one important point here, that in the triode region, your gain will be fixed, will be almost 0. Not only that, your output voltage will be also fixed and will not depend upon the input voltage, and that is the reason, as I explained to you, you will always get a constant value of output voltage independent of the input voltage. This is one thing which I wanted to propose at this stage. So, looking at the voltage transfer characteristics, I can only therefore safely say that whenever my gate to drain, so if I want to bias the device as an amplifier, it is always advisable to keep the device in the saturated region. This is the one takeaway which you should do from this discussion. You place it here or here, you are in a problem. You place it in the saturation region, which is this region, you automatically get a very high gain which is available with you, and this gain is typically very high, right, of the order of few 10 to the maybe 10, even 10 to the power 2, 10 to the power 3 voltage by doing certain manipulation, of course, and you can do it, right. Okay, with this let me explain to you what do I get from here. Now what I want to tell you is that since we have understood where to bias the device, say you have biased the device somewhere as expected, you have biased the device somewhere here. So, almost in the middle of the region, and this is your VIQ and this is your VOQ. So, output Q, input Q, which means that you have to bias it by an external DC source, right, so that initially even without an input signal it is placed somewhere in this region. Please be very careful, this is very important, that you need to first of all bias your device to sit in the saturation region before application of any input signal. That is that's what I was trying to tell you, and therefore if you look very carefully this expression here, that my overall gate to source voltage, which is a function of time, will be the DC bias which you put VGS, this is the DC operating point, and the input voltage. So, this is my time varying input voltage, maybe an A sin omega t sort of a input voltage, and you do have VGS, which is basically the DC bias, which is fixed bias which is available to you, and you add just simply to that and you get this. So, this is basically a small signal output, right. Now, the output voltage to be a linear function of the input voltage, the transistor must be biased in saturation. This is the one single point which you should be very careful, right. Now, what you do is that you apply a symmetrical sinusoidal signal to the input of an amplifier, and we get a symmetrical sinusoidal output in the output side. So, you apply maybe a sine wave like this, and you automatically get in the output side an amplified sine wave in like something like this, 180 degree phase shifted, fine. So, this is one important point which you should be very carefully take care of in all due respects as far as this device is concerned, right. Now, let us see as I discussed with you in our earlier discussion, that the load line plays a very important role. Why? Because the load line tells you those points within the IV characteristics of the BJT or the MOSFET where you should bias your device for proper application of amplification, right. So, you should be very careful of the load line analysis or load line as such. As I discussed with you, this is the Q point. So, this is your input, and input goes from like this, right, and your output goes something like this in the time domain, right, and you can get, sorry, this is the input which you get, and you get this is the output which you get from the this thing. Now, the idea here is that let us suppose I was discussing with you earlier point, let us suppose you had biased the device, this is my IV characteristics of my BJT, right, this is my IV characteristics, you had put the load line something like this and you biased it here, right. Once you biased it here, well, it is pretty simple, then you apply an input signal, this Q point goes to this, suppose there are a large number of curves here as well, it goes to this point. So, this is your Q, this is your Q1 and this is your Q2, right. So, it goes to from here, so from here it goes to, let me say, it goes to Q1, right, then from Q1 it goes to Q again, and then Q to Q2, and then again Q2 to Q. So, one single transition of input wave cycle will make my Q point traverse 1, 2, 3, 4, agreed. But if this signal itself is a very large signal which is this much big peak to peak, right, then rather than going to Q1 it might actually go to this place or even go to this place, fine, you getting my point. And therefore, it is quite interesting or important to add that your input signal should be as small as possible or really small in nature. Otherwise, you force the Q point to go to the in this case into the triode region, and in this case if you go down into the cutoff region in cutoff, which means that once you go to triode or cutoff, triode will ensure that your gain is a non-linear amplification is there, which means gain becomes a function of your voltage. Please remember, you can see that, see this is current and this is ID versus VDS. If you see here the resistance is varying. If the resistance is varying, obviously your gain will vary, and as a result if you force your device to be triode region, you end up having a non-linear amplification, whereas if you force the device to go into cutoff, your output voltage will be clipped. So your output should have gone something like this, but what happens is that because of cutoff this goes like this, right, you have cutoff here, this is cutoff. So this is also known as clipping, so you have clipping taking place. So you need to ensure that your device biasing is very proper, right, and that is what is the next topic which I want to come to. And therefore I was saying that if the input output exceeds this limit, a portion of the output signal will be clipped and the signal distortion will take place. Now this explanation of this idea which I was discussing with you, let me explain to you the various biasing techniques which are available to us as far as MOS device is concerned, right. The first biasing technique which people used to follow much earlier, obviously a very good not a very good biasing technique, is what is known as a fixed, first is the fixed VGS technique or a fixed gate to source voltage. It is not very good, of course, not good, which means that in fixed VGS what do you do, that you have got a drain source voltage, you do like this and then you fix up a gate voltage here and you fix up VGS, right, as I was discussing. So this is basically a grounded source application with RD here and VDD here, this you have been learning it till now, but the way it has been done is that you fix the value of VGS to be in saturation region. But the problem is that if you suppose replace this BJT by other BJT, if you replace this RD or VDD, then chances are that the Q point will shift. So what might happen is something like this. So you have one device, so if you plot ID versus VGS, let us suppose VGS, and then if you plot it, then this will be this and maybe this. So this is for VGS1, let us suppose, and this is for VDS1 and VDS2. So even if your drain to source voltage varies, for the same values of VGS, two devices might be so different from each other that the current obtained will be so large, so different from each other. It might also happen that for one calculation you have done properly, for other one when you fix up the MOS device, it forces it to go into saturation region or the linear in the non-linear region. So fixed VGS technique is not a very good technique and has been often like we do not assume it to be a very good technique. The second one which people follow is defined as source degeneration technique, right. This is source degeneration technique of biasing. So what I am trying to do, I am trying to bias it from an external source, right, using a DC bias. I am doing it on external source and trying to find out. Let me draw for you how it is different. It is exactly the same as the first case. The only thing is that here we are adding an extra source resistance in series to your RD and VDD. So I have a VGS of course available here. If you write it, so this is the value of VG. So if you write its VG, this will be nothing but VGS plus ID times RS. This is the value of VGS here. This is VGS and this for VGS plus ID is the current which is flowing here. So ID into RS is the voltage drop across these 2 points. You add this voltage drop with this VGS and you get the total gate current. So the total gate current is therefore made up of VG minus VGS. Therefore since VGS is almost fixed, I can safely write down that VGS will be equals to VG minus ID RD, right. Now what happens is that, say if you assume that my VGS has to vary for a fixed value of VGS, even if ID varies because of some reason or other, then my VGS will also vary in the opposite direction in order to compensate for the variation. I will just show you how it works out. Say ID was say 1 milliamp, right. So 1 milliamp multiplied by RD, say 1 kilo ohms, right. So this if you multiply these two, I get 1 volt, say VG was equals to 3 volts. So 3 minus 1 is 2 volts. So VGS was equals to 2 volts, right. Now let us suppose this becomes 2 milliamp. So 2 into 1 is 2 and I get this to be 1 millivolt, and therefore VGS from 2 volt it becomes 1 volt, right. VGS becomes 1 volt, which means that with increase in current the gate to source voltage reduces, and therefore it helps you to reduce the current. So this is basically a negative feedback control, negative feedback control. So I will explain to you just now how. So current is flowing, so this is basically at higher potential as compared to this, of course. As a result, this will reverse bias my source gate junction or the source. So it's something like this. On the source side it is source side, right, this is N plus, let us suppose, and this is N plus drain side. I have a gate here and then I have a metal function here, and then I have got something like this, right. Now what I do on the source side, I apply a positive bias now. So what happens, the depletion thickness will be much larger here. If you did not apply any bias, it will be something like this. If you now applied a bias, which is basically the RD into ID into RS, the depletion thickness will become more stronger, and therefore your current will drop down. So what happened, you increase the current, right, and the decrease in VGS forced the current to go down. So something like this, it is if you plot ID versus VDS, your current increased. So what happens was, your VGS was large, you had a large ID, you force the VDS to go low and it forces the current to go low here, and so for the current becomes something like this. So you had I1, I2, I2 is much smaller as compared to I1, and automatically you get a much more stabilized system. This resistance is known as the source degeneration resistance. This is known as source degeneration resistance. Higher the value, better the control is, right. The cost you, let us also understand the cost you pay for it. The cost you pay for it is that there is a voltage drop here, right, and this voltage drop can never be recovered, right, and therefore the overall leg room. So you have a headroom and a leg room. Your headroom is basically, say you are applied VDD is say 5 volts, right. Now whatever you do, the output voltage cannot go beyond 5 volts, then otherwise you will be violating Kirchhoff's law and they will be clipping, right. Let us suppose due to amplification the output peak voltage goes to say 3.5 volts, sorry 3.5 volts, then the headroom available to you is defined as 1.5 volt. This is known as headroom, fine. Also we define legroom. Legroom is when you go to the bottom side. So if you have a current flowing through the device and your bottom should be actually grounded, but you are going to a value say equals to 1 point, say your maximum value you are going to say, the value you are going like this value is say 0.5, then the legroom available to you is 0.5 volts, and you can play with it. Now if you already have ID into RS drop with you, then this rather than 0, this will look something like 0.5 already. So you have actually eaten away into the legroom of the device. So the price you pay for it is that your peak to peak swings are therefore restricted now for a source degeneration technique based biasing, right. So you be very careful about this technique, that though you gain something you also lose something. Two things before we move forward. Okay, so let me go to the third one. Third technique for biasing is basically your drain to gate feedback technique, drain to gate feedback, right. It is basically drain to gate feedback. So let me draw for you how it looks like. It is something like this, right, and you have this. So RD, RG, this is VDD and so on and so forth. So I get VDD equals to VGS plus IDRD, of course, but if you go by this technique or from this path, I guess VDD equals to ID times RD, right, is it okay, and you will also get IG times RG, but IG is very small, you do not have any gate current available with you. So I get, therefore even if you follow this path, the voltage drop across this will be negligibly small, right, and you will get so a very idealistic situation. I will get therefore VGS to be equals to VDD minus IDRD. What is the advantage of having a feedback loop here which connects gate to the drain end is that typically now your gate and drain are bound by this RG. since Ig equals to 0, the voltage drop across this thing will be negligibly small. So, I could expect the gate voltage to be approximately equals to drain voltage, and therefore, this device will always be in saturation whatever be the input. So, this is a quite interesting phenomena which takes place, that since your gate and drain are shorted right, then what happens is that you force the device to be in saturation for all values of VGS, right, and this is what you get. The fourth technique, I will not discuss it here, is known as constant current source technique, right, that has been used quite often across the board, but this is the constant current source technique. Please understand one more important point before we move forward, is that whenever suppose we draw maybe a source degeneration resistance based design, right, then if this is the gate voltage which you see, this is the output here, we have a gate voltage we apply here, right, the input is given here, and then we have a gate voltage here VGS, CB we write down, and then CC, and this is VDD. We have got two types of capacitors here, right, and these capacitors are also known as blocking capacitor CB. This is known as blocking cap, blocking capacitor, and this one is known as a coupling capacitor. So, please understand that once we have this BJT biased at the saturation region, I do not want it to move away from the saturation region by external DC source. Now, any power supply, in this case VGS is a power supply, any VGS which is power supply will always have some DC component superimposed on the AC component. It will not be pure AC which you will get, right. Now, that DC component should not change the Q point of this MOS device, right. This MOS device Q point should not be changed by the DC input of this VGS. So, what people do? People put a capacitor here. Once you put a capacitor here, remember the reactive impedance of the capacitor is 1 upon j omega c. So, your omega when it is 0, xc is infinity, right, and therefore, for a DC bias which is omega equals to 0, the reactive impedance is 0, or the capacitive impedance is 0, is infinity, and therefore, it does not allow any DC source to go here, and it looks very good. Similarly, when you have a coupling capacitor, then I would like to see that all the AC signal which is available here should go to this next point, and all the DC bias coming from VDD should be stopped. So, you put a coupling capacitor, same principle you apply here as well, and your V out therefore will be pure AC, and there will be no DC bias available with you, right. So, these are the blocking and coupling capacitors which we seldom used while while biasing our circuitry, right. So, please be careful when we discuss the biasing of circuitry for all practical purposes. With this, let me discuss with you that okay. So what happened was, so let me see therefore what happens, that now I have a VGS, right, I have a VGSQ, I have a DC bias which is somewhere in the middle, I have a DC bias here, and DC bias I am overwriting the input voltage Vi. This is my AC bias which I am giving, right, and this is my total current or total voltage is sum of the DC voltage here plus the input AC. So, I get VGSQ because it is at Q point plus VGS, gate to source voltage. So, instantaneous drain current Kn is nothing but mu n C oxide W by L, right. So, this is the Kn value, this is Kn. So, ID equals to Kn VGS minus V threshold voltage whole square in the saturation region, and therefore, ID is equal to Kn. In place of VGS minus VTN, you just have to put this value now. So, I get VGSQ minus VTN plus VGS whole square, you got the point, because just in place of this I place this, and I get, now if you expand it, I get something like this, right. This is no problem because this is we have been talking about quite a lot of time. So, it is VGSQ minus VTN whole square, the current in the saturation region, no problem. This is also no problem because current is a linear function of VGS. Where you have a problem is the last part, where the current is a parabolic function of VGS, which means that if VGS increases by delta VGS amount, the current will be parabolically increasing. So, there will be heavy non-linearity provided you have this component of the current available with you, and that makes the life difficult for overall picture. So, for a sinusoid, that is what I was saying, for a sinusoidal signal, input signal, the square term produces undesirable harmonics or nonlinear distortion in the output side. So, to minimize this distortion, we require that VGS should be as small as possible. How small? Much smaller than 2 VGSQ minus VTN. So, you are into deep triode region now. So, therefore, if you neglect, therefore, in such a scenario, if you left it VGS square, I get ID equals to IDQ plus ID. The AC drain current is given by this quantity, we have already discussed this point, and therefore, I get GM is defined as rate of change of drain current with gate voltage, which is nothing but this, because if you differentiate with respect to gate voltage, this vanishes off and you get this. So, GM we get 2 times K times VGSQ minus VTN, and this is what is the value of transconductance which you get, right. So this is what you get from the basic fundamental principles which you get. So, let me stop here because of the want of time. What we have understood today is, given a MOS device, right, where can I place the MOS device to obtain the most linear and the best saturation, first thing, and the second thing is how to bias it using a DC source from an external world. From the next turn onwards, we will look at the small signal model of MOS device, and then we will look into the various modes of operation of MOS device, common source, common gate and common drain. That will take care of our almost the analog part of the MOS device, amplification part at least, right. Thank you for your patient hearing. Thank you.